Good afternoon, everyone. Welcome to this session. I am Vasu Chari, a Principal Solutions Architect with AWS, and we are here today to talk about large language models. Few companies build large language models, and fewer still built one before ChatGPT. The challenges are many: high cost of infrastructure, availability of GPUs, the talented team required to train the model, and more importantly, access to a large corpus of high-quality data. Bloomberg, as one of the leading data providers to the global financial services industry, had all the data it needed and a well-established team of data scientists and engineers. As a research project, Bloomberg trained its own large language model, BloombergGPT. Today, you're here to learn about the challenges they faced on their journey, how they overcame them, and how their experience of training an LLM on AWS has informed the company's approach to using generative AI in its products. We are joined today by Phil Vachon, Head of Infrastructure in Bloomberg's CTO office, and Vadim Dobrovolsky, a team leader in Bloomberg's AI engineering group, who is also a co-author on the BloombergGPT paper. Please join me in welcoming them. Oh.
Thanks, Vasu. Appreciate it. Good afternoon. I can't really add anything to an intro like that, so thank you, Vasu. As Vasu noted, at Bloomberg, we decided to train our own large language model. And we're here to share some of the lessons we learned building and training that model on AWS. So we'll talk a bit about how Bloomberg navigated these challenges across the process, including managing massive volumes of data across a large network of GPU nodes. We'll look at how automating and templating that infrastructure helped us, as well as managing the data storage and data transfer. After all, we wanted to protect that data. Our data is our lifeblood. And keeping all these things secure while rendering the training process less error-prone, and all of which really helped us launch model training projects more quickly, thereby enabling rapid innovation and product development. So I think it's safe to say most of you know Bloomberg, but I'm pretty sure many of you don't know that Bloomberg has been using various forms of AI to serve our customers since 2009, enabling us to provide market-leading insights. We've always maintained a very strong research presence in the AI and NLP space. In fact, our team has published over 100 research papers in the last 3 years, and we're always looking at new ways to provide these unique insights to our clients, helping them find those needles that they're looking for in that financial haystack. So I want all of you to turn your memories back to 2020, maybe not the bad parts of 2020, and remember a time before we were all talking about ChatGPT, GenAI, all that fun stuff. So turning back the clocks to 2020, remember that time, and a large group of researchers from OpenAI were charting new territory in this large language model development. In fact, they released an exciting paper on arXiv titled "Large Language Models Are Few-Shot Learners," heralding the development of GPT-3, a 175 billion parameter model. As this technology emerged, and as all of us were sort of starting to figure out all the cool party tricks we could do with ChatGPT, we also, on the research side, we're starting to understand that the number of parameters, at least we believed, were proportional to the quality of the model's performance. Of course, this performance is proportionate to how much training data, so how many good tokens you have to feed into the model, and how many GPU hours you are willing to spend actually scaling this up. One of the things we are actually starting to note, I want to say, is that the scaling laws, as we know them, may not actually be scaling. And we're seeing, as the number of parameters increases, that ever larger LLMs are actually having diminishing returns in terms of performance. But the details of that are a completely different discussion. So this paper lands, and everybody scrambles to buy GPUs. And of course, GPUs become even harder to get. And then, of course, at Bloomberg, we're really starting to see the potential of LLMs. Like I said, we've been looking at AI as a way to provide value to our customers since 2009. And we've had these problems that have always been of interest to better support our clients. For example, how could we provide reliable summarization? Or how can we make it faster to conceptually search for a large pile of information for specific documents, and so forth. So, as we evaluated the experimental results from the GPT-3 paper, they were impressive, but 175 billion parameters seems daunting and even unachievable. This actually even begged the question from our perspective of whether or not it was even necessary to have a model that was that large. And then, of course, we started looking at the volumes of training data that we had available to us, and we needed to think about GPU time. And by the way, GPU time was precious. Our team started asking an interesting question. Knowing that financial professionals, we have a unique argot we use when we're talking about things. Could we actually use this to our advantage and train a model that actually is specialized for financial services applications? Does it even make sense to do this? And famous last words, how hard could it be? We knew there was another risk we wanted to at least understand. These probabilistic models, as we will talk about a little bit more later, tend to get things wrong. This certainly isn't something that's acceptable for our customers. They expect us to be right most of the time, if not all of the time. We didn't really have a great idea of the circumstances where we could take that risk, where maybe an error is okay so long as you can give a user a hint that that error was there. And of course, we didn't even know at that time how we could mitigate this risk when we were designing systems that integrate large language models. So what better way to do this than to build and train our own GPT-3-like model for experimentation? This would let us actually research ways to build applications around a large language models and give us a baseline to compare its performance at the time to other existing and emerging techniques. And of course, the obvious questions at the time: how does one train such a model? Where does one get sufficient compute capacity to perform that training? And since GPUs were the best way to do so, how do we get these GPUs? Of course, we're in the middle of a global semiconductor crisis as well, and we experienced this across other parts of our business, but GPUs were especially hard because of this extra strain. So we've decided to train our own large language model, and so maybe you are thinking about this too. So due to this combination of extremely high demand for GPUs, the COVID-induced supply chain chip crunch, and it really just meant that getting GPUs was quite challenging, practically impossible in some respects, and the lead times we were talking not 6 months, 9 months, 12 months, but maybe 24 months to get GPUs in hand. Of course, we do have GPUs in our data center, but we're using those GPUs to serve our existing applications. So would we be willing to trade off the capacity to keep our clients using the insights we're providing today with the process of training a new large language models for experimental purposes? Of course, that's not really a trade-off when you think about it. So undeterred, first we started taking stock of what training data we had. And we had a combination of generic and mixed domain content and a specific curated set of finance-specific data. We actually took this and did some calculations and figured out we had about 700 billion tokens available to us. As we optimized all these parameters, we determined we would need about 1.3 million hours of GPU compute time on NVIDIA A100 GPUs, then the top-end product, producing a model with 50 billion parameters. It became pretty clear at this point that we were going to need some help to get this done. AWS was the best and fastest way for us to get this going. We knew that GPUs were available. We could get reservations. And we actually had the knowledge or we knew that AWS was building up the capabilities we would need as well. We, after all, had a small team, and we wanted to make sure that our team was able to be enabled with good tools off the shelf. At the time, the P4 EC2 Ultra cluster was what we landed on. We were using high-end A100 GPUs, as I said, and the Ultra cluster also provided the high-speed and low-latency connectivity intra-node as well as inter-node necessary to support model training. And we'll get a little bit more into why this was important later. Although for those of you who've been living in the world of HPC, I think you can guess. So working with AWS for model training was actually a no-brainer. All the undifferentiated heavy lifting related to training our model was taken care of by Amazon SageMaker. SageMaker provided for us a fully managed service, a native parallel training framework called SMP. SMP diverged, of course, from PyTorch's FSTP, which for us was actually a challenge because we have an on-premises platform, Bloomberg's internal data science platform, which uses PyTorch for all of our training and all of our inference. So this means that we did have to rebuild our training code to support that API. But this seems like a pretty small price to pay, given the fact that we couldn't even get the GPUs to enable training. We also were able to get the allocation that we needed. We were able to schedule the the P4D 24x large instances when we needed them. And each node featured 8 NVIDIA A100 GPUs. With each GPU having 54 billion transistors, well, that's a lot of transistors in a single box. And then it's important to stress that at the time, software, drivers, even the hardware all had reliability issues. So having a partner who could take care of this nitty-gritty detail was really important. We wanted our team to focus on model training, not debugging things. In addition, having someone with a staff of experts with whom we could share knowledge, experience, even validate ideas with was key. Because of this tight relationship we had with AWS, we were able to pull this training feed off with just 9 AI researchers. That's right, just 9. If you look at the number of authors on the GPT-3 paper, I think it was closer to 100, that's something like that, 75. So yeah, a lot more. Of course, then you have to start thinking about, well, so some of these decisions we made about the size of our model, the algorithms that we were choosing to train the model, the techniques to de-risk training, all kind of factor into how you design this infrastructure. So 700 billion tokens, that's about 3.5, 4 terabytes of data, needed to be stored somewhere securely and reliably, because like I said, our data is our lifeblood, so we don't want someone walking away with that. And we also need to keep the A100 GPUs fed. They're hungry for data, and you need to be feeding them tokens at high speed all throughout the training process. You also have to remember that we wanted to make sure we didn't have to start the training process over again from scratch if we hit an error. So we go through a process called checkpointing. For those of you who haven't lived in the world of HPC, checkpointing is the process where you're capturing the state of a long-running process. And in this case, it's your latest model and optimizer states on a periodic basis. Of course, this has a cost. While you're capturing all of that data, and while you're actually collecting it and doing all the I/O work to store it, you are actually leaving your GPUs idle. That is leaving precious GPU time just sitting there. Fortunately, the P4 Ultra cluster provided exactly the right connectivity, both NVIDIA's native connectivity technology in-box, and then which is the NVSwitch intranode connectivity, as well as the connectivity between nodes, the EFA, Elastic Fabric Adapter, with curl bypass, gave us just the right combination of I/O and IOPS, as well as latency. And then, of course, the infrastructure needs to be reproducible and rebuildable. ClickOps feels easy, it's nice, it's instant gratification, but the moment you have to go and recreate an environment or audit an environment or apply broader controls to an environment or just do any small change that might perturb lots of aspects of the environment, you find yourself doing a lot of manual labor. And then there's other things like warm pools of resources, and then the automatic job recovery services all benefited from an infrastructure as code and an automation-first approach. And of course, nobody really wants to wake up in the middle of the night to kick a training job to start over again because of a hardware failure. So the more of this you can automate, the better off you were. All right. So I want to bring up Vadim now, who did a lot of this interesting work. Vadim.
Hey, everyone. So we roughly knew what we were up against, but how do we put this in motion? Turned out putting this in motion was fairly straightforward through the power of standard AWS building blocks we used at that time. A lot of enablement services such as S3 buckets, VPCs, IAM policies were already well understood, and we have pre-built Terraform components. However, one missing piece for us was learning the Amazon SageMaker itself, and that's where AWS account team was very helpful for us to establish this common understanding. Now, one important detail I want to highlight on this is the internet-facing access of your training cluster. You probably ask yourself, does my training cluster need to have access to the internet? And the right answer is probably no. That's why I invested quite a bit of time to ensure that all our infrastructure is network isolated from the internet. And we'll talk about this later. However, before beginning, we also needed to consider some of the specialized AWS services, especially around data management. Because the data stores and databases you typically use in a free tier web application won't quite cut the mustard. For starters, our training data set was roughly 3.5 terabyte, and our checkpoints was 600 gigabytes each. And we wanted to produce and store the checkpoints as soon as possible, because as Phil mentioned, during the checkpointing, our GPUs were idles. And we needed to produce these checkpoints every 2 hours to avoid the considerable training progress loss. So we needed a high throughput, low latency access to the training data. We of course needed to apply the right controls to our data. Data needs to be backed up, and the high-value data needs to be protected with the right access policies, or even customer-managed encryption keys, and made readily available using the standard tools. For this, we ended up using Amazon FSx for Lustra to manage our training data through the training process, and then we used S3 as an online backup storage solution, and we kept them in sync. That provided us with the guarantees that our training data is not only readily accessible, with a low latency and high throughput, but also has all necessary security controls applied. Training data sets are very valuable resources. In fact, the training data sets we used for training is also the training data we deliver to our customers. We don't want to accidentally expose this data to the unknown stranger on the internet and let them walk away with this data. Proper resource policies combined with encryption in transit and at rest make it easy to ensure that only services that should have access to read and write training data will be able to do so. The compute time, such as GPU allocation, is also a precious resource. Heaven forbid someone can steal this GPU capacity from us, or even worse, we have the unauthorized employee who is doing something with our GPUs. Putting into place monitoring, who is accessing, how, and when, was important for us to make sure that our GPU resources are not being wasted. All in all, we need to apply the enterprise best practices, a theme we all have invested in as we improve our practices of using public cloud to host our most sensitive workloads. Now, LLM was, at that time, and still is, a rapidly evolving domain. Making it easy for researchers to spin up experiments, fail, collect the learnings from fail, and quickly iterate is essential. Best practices when it comes to security and compliance should not be a hindrance for our researchers, but rather serve as a foundation to build on top. Now, large-scale training jobs present a number of operational challenges. It is a distributed, stateful, very expensive workload, which shards hundreds of complex computations across hundreds of nodes, and doing this for months at a time. The virtually unavoidable failure on a single node must be handled gracefully and, when possible, automatically. Needless to say, the training job is a very expensive resource, so cost and resource efficiency are paramount. That's why we spent on planning our operational stack before starting our first large-scale experiments. So for this, we introduced a notion of recoverable and non-recoverable errors, and then depending on the type of error, we implemented different remediation controls. To implement remediations, we extensively used SageMaker native integration with a CloudWatch log and metric management solution. And then to automate the remediation procedures, we relied on Amazon SNS and AWS Lambda to kick off the downstream actions. We discuss on the next slide some of the operational issues we specifically faced during the training and which may be interesting for you as well. So one of the first failures we experienced was the underutilization of GPU resources. At that time, we used NVIDIA A100 chip, which provides 312 teraflops of compute capacity. This is an amazing number if only thing you're doing is multiplying multiple numbers. But in the reality, you rarely will be able to achieve this theoretical throughput of your computations because of various factors, such as network synchronization, transfer between host and GPU memory, storage I/O, and others. So in order for us to understand how efficiently we're using these powerful training clusters, we instrumentalize our code to gather the efficient T-flops across all nodes in our training cluster. We then added the remediation control to monitor what is the effective T-flops per GPU across the cluster during the training job. And if this value dipped below 50%, we stopped the job and we investigated to understand how we can improve the efficiency. That helped us to save some time and money early on when we debugged our training script initially and understand what is our global training bottlenecks are and how we can address them. And here's a helpful data set for you. So for the duration of training job, after applying some optimizations, we ended up having roughly a little above 100 T-flops per GPU across our forward and backward paths. This is not 100% of capacity, but it's still a considerable chunk. Another failure mode worth mentioning is the training convergence. So when we started training the BloombergGPT, there were very few initiatives in the world where the teams did a large model pre-training and published the results publicly, right? One of the notable examples was Big Science. Kudos to them. So the training software and the training hardware stacks were very brittle at the time, and the model architecture and tokenizers were evolving pretty much every day. So we as a team, we understood that we should anticipate the challenges with our training job convergence. However, it was not clear for us what kind of challenges to accept. Then again, smooth seas don't make good sailors. So that's why we built the operational capabilities into our training script so we can capture the internal state of our model and optimizer on every step and stream these metrics to the CloudWatch. And we're talking about megabytes of data, of operational data streaming every minute for the duration of months. Now, thanks to this instrumentation, it helped us to understand our initial convergence issues. So around 12K training steps, we saw that the model, the loss curve, started flattening, which typically indicates that the model stopped learning. So the next step for us was to understand what's happening inside the model during this time. And for this, we streamed the internal activations, model weights, gradients, and gradient norms to the CloudWatch. And as a result, we were able to identify the root cause, which turned out to be the gradient explosion problem on one of the early layers of our network. And it helped us to remediate. On the screen here, you can see that one of these pesky lines is going up after the 12K. This is the manifestation of this gradient explosion issue, which I talked about. Now that we discussed the training infrastructure and how we built the training clusters, let's talk about what we learned from this.
Thanks, Vadim. So all that work, well, we had to get something out of that, right? And we did get something interesting, the BloombergGPT research model. We found, and this is one of the key results, we found that our model, when we were experimenting, did better on finance-specific tasks than general-purpose models that were available at the time that had far more parameters. If you get deep into how BloombergGPT was trained, and some of our experiments that didn't work so well, if you want to get deep on that, you should have a look at the BloombergGPT paper on archive. Our team learned a lot of hard lessons along the way. We were fortunate to have partners in industry and a great team at AWS to help us brainstorm how to get over these humps. But if we can save you from having to learn these lessons yourselves, definitely check it out. It's important to remember, and I want to be clear about this, BloombergGPT was actually never intended to be used in any sort of production applications. The model was actually an experiment to help us explore how to build applications that integrate LLMs. And this gave us a lot of experience and insight, because at the time, a lot of us were not really thinking about the LLM and how it fit into the user experience and workflow and all that. The agent-based model and the chat agent-based model that ChatGPT popularized maybe isn't necessarily the most effective application of that model. All right, so because we actually wanted to figure out exactly how to build products and applications around generative AI, having BloombergGPT was extremely helpful and powerful for exploring this. And really getting the experience and insight we needed to figure out how GenAI actually could help us build better products. So out of this whole effort, we developed 3 guiding principles for how to make use of LLMs in our products. And for us, this is absolutely driving our roadmap around how we adopt generative AI for products facing our customers. First is that any of the outputs from the model must be derived from trustworthy sources and must reflect reality. We all saw the examples where people were having Google's model tell them that they should glue their cheese to their pizza. We want to make sure, though, our clients are actually finding valuable insights. We want them to trust our accuracy, because that trust is extremely important in supporting them in their research and in their analysis. It would be unacceptable for such a source to sneak in. After all, we don't want to send someone off in the wrong direction. We've all seen those cases, like I say, where people were tricking models into doing crazy things or suggesting crazy things. Next, you have to think about the fact that the LLM is not actually a standalone system. It's actually a part of a larger product. It's a part of an application. It's part of something that a user interacts with and derives value from. So we have to evaluate the model itself in the context of how the user is interacting with it, interacting with the system, interacting with the application. And also, we need to be able to pull in what is a user expecting to get out of a system like that. We need to provide steps to help guide users to use these applications appropriately. So we don't want to just have a free-form text prompt or something like that as the normal use case for the majority of our applications. And we want to provide the proper user experience hints, giving people ideas about where a model might have hallucinated or might be wrong, or even better, giving that user an actual breadcrumb to where the model derived that particular data point. We need this information. We also need the ability for users to give us feedback about the quality of results. So we need to make sure that users have a quick, low-friction way to provide that feedback so that we can then integrate that information into evolving our product and understanding and measuring the performance of the model as well. And of course, the most important principle, and one that I really stress a lot, is, as I was saying before, we really need to make sure we provide transparent attribution to where the model is getting its data. We need to make sure the user is able to see the original source, the reason why the user was given a particular output. We need the user to be able to interact with that output as well. And we want to make sure that the users have enough information to evaluate the accuracy of that answer at their fingertips. After all, context is everything. Furthermore, we need to make it really easy for those users to flag and give us that feedback. Like I said, I can't stress that enough. That information is essential so that we can make those fixes along the way. So I wanted to talk a little bit about some specific ways at Bloomberg we are actually applying large language models and generative AI. Like I said earlier, LLMs have so much potential, and building impactful products around generative AI requires a lot of forethought and a lot of really thoughtful product development. Early product offerings across the tech sector were kind of like throwing different applications and different approaches against the wall. The agent-based approach obviously being one that a lot of folks saw as an immediate use case. But of course, a lot of these showed varying degrees of quality and reliability. And at Bloomberg, we really didn't want to put a product in front of our customers where we'd have questions about that. So as we've been focused as a company on building trust and trustworthy products and impactful products for our clients, we're always really cautious and pragmatic about how we build applications that could actually work against us in that regard. So I want to walk through a particular example. So research analysts in the equities space especially, they're going to have questions they're going to want to ask about the environment. These questions could be very simple, like, let's say I'm an analyst that's preparing a report so someone can make a trade about an entertainment-focused portfolio. For example, I might want to quickly know the answer to the question, Walt Disney's closing prices for the last month. So as our client at Bloomberg, you would be able to use Bloomberg Query Language, or BQL, our standard tool for providing access to our massive depth of historical and current market data. And of course, you'd be able to use this language to get, for the DIS, which is the ticker symbol for Disney, you'd be able to get a table of values for the daily last price for the last month for Disney. This straightforward question could be written as a simple BQL statement in this case. Of course, you might want to marry that information or very different aspects of information about a particular symbol or a particular equity when it trades. There are many useful data points behind any equity, any symbol, that you might want to take into consideration. For example, the volume of that equity that's being traded. You might want to use that as an indicator of market conditions or sentiment, or even just understanding the change in behavior of an equity around a particular announcement or whatever it is. So let's say you want to understand the volume curve for Tesla over the last 5 days. Again, a very simple question can be written as a very simple BQL statement. In this case, we're just asking for a roll-up of this data. And of course, this is like a really simple query again that starts bringing more features of the BQL query language to the front. Of course, the number of questions that you might want to ask get ever more complex. And the number of features that you might be using in BQL might get more and more elaborate. And in fact, you can integrate very in-depth calculations across a particular symbol or group of symbols or whatever it may be. And if you start looking at, for example, calculating a Sharpe ratio or getting a ratio of by analyst recommendations to total recommendations for holdings of Starbucks. Again, you can do all this with BQL, but of course you would have to make sure that you become an expert in the BQL language. This can be pretty daunting for an entry-level analyst or someone who's just trying to quickly understand the answer to a question that they might not already know how to do this with BQL. And if you're one of us folks who are lucky enough to have a background in writing software, learning BQL is fairly straightforward. In fact, probably many of you can intuitively understand what it is that each of these queries are getting at. However, as you get more complex in what you're asking for, you're going to have to delve further and further into documentation and understanding the data model behind BQL and all that. Hit the books, learn BQL, and then come back and then start answering these questions. That doesn't sound like the most efficient way to do things, though. So what if, instead of actually having to write the BQL query, I can just think about the question I want to answer about that particular security? If we can make it easy to generate a query just from some natural English content, and then generate a BQL query that answers that question. So starting with a very simple question, I want the revenue growth next quarter for Ford and its peers. And right off the bat, I can tell you that query is not going to be a very straightforward BQL query. That will require a little bit of depth on how to use the language itself. So now we can have our large language model, which in this case is a fine-tuned model. And that model has been fine-tuned specifically to help generate and understand BQL queries. So the model is able to generate this BQL query, and it knows what a peer is. It knows, basically all the different terms that you could actually include in that query. And then along with providing that query in the user interface, we also provide a table, a tabular view of the results. So what we're doing here is we're allowing the user to give a natural language prompt. We're giving them the query, which they can actually then edit free-form themselves, and then giving them a tabular view of the results so they can evaluate whether or not that answers their question or just see the information that they were looking to get at. So I want to make it clear, this is an off-the-shelf, open-source, open-weight model that we're using, and basically by investing in fine-tuning this model, we're able to reliably generate BQL code, which then can be turned into a formula in Excel or Python or in our bquant environment, thus making it easier for users to get access to our data. So another area we're very interested in, of course, is gathering and synthesizing insights. This could be providing summarization of a very long earnings call transcript, for example. So for those of you who are working at publicly traded companies, you're probably familiar with the regulatory filings and the various rituals you have to go through on a regular basis as a publicly traded company to provide the transparency to investors, helping them understand the risks and whatever fundamentals there are about the company. So these quarterly earnings reports, these filings, these calls, whatever it is, these are hours-long calls in these cases. There's reams of transcripts, tens of thousands of words, hundreds of pages. It's a lot of work for a human to go through. And of course, all of this is full of finance-specific jargon. So especially during earnings seasons, you can get some very interesting ways that people term things that you might want to be able to dig into. So analysts should be able to get to the key insights in a transcript as early as possible. So on the left side of the screen, you can actually see some findings, some key guidances that were generated as an automated summary from this particular Q3 2024 earnings call for Apple. And our goal is not to provide a full summary of an earnings call, but rather to answer the questions that a typical analyst might have about this call. So in designing this system, we chose to use RAG, the Retrieval Augmented Generation paradigm. And what we did is we went to our own in-house analysts. So we have a very competent team, the Bloomberg Intelligence, or BI analysts, who have decades of experience in the financial services industries. We're answering these types of questions for financial services companies. And they have very intimate knowledge of how, though, our clients operate at a fundamental level. And we wanted them to help us train a system that would consist of a large language model and a list of questions that are kind of common questions that an analyst would answer. And then we wanted the model to provide high-quality summaries of those of the answers to those particular questions. So we needed to make sure that the answers were provided, and accurate for several transcripts. So we had to test that. And of course, as we evaluated the system's performance and generated summaries, we found, of course, that we were able to successfully get to the point where we were satisfied with the quality of the summaries that were provided in the guidance section. Now, what was also really important is rather than just giving the summary as a standalone bullet point, we actually provided then the way for the user to click on one of the particular guidances in the automated summary, and then actually expand that to where that was found in the document. So we were able to actually provide that level of transparency so that a user would be able to actually understand the context where that insight was derived. So when the earnings transcript arrives in our system, passages relevant to each of the seed questions are retrieved using a semantic match against sparse and dense vector indices, and summarized answers are then produced by the LLM. These summaries are then run through some post-processing to enhance the quality of them, but the important part is, of course, that every one of these summary points can be evaluated by the user. Again, we want to provide those breadcrumbs, those hints to the user so that they can make that decision. And of course, as a part of our overall use of AI, machine learning, natural language processing, we have a lot of quality control mechanisms in place in general to manage and monitor the performance of the models. And we do this at release and, of course, post-release. We're continually monitoring these things. So this was 2 years ago. And when you're thinking about it, how we did this 2 years ago versus how we do this today, well, 2 years, a lot of things can change. So one of the things I wanted to highlight is so many of the things that Vadim mentioned that we had to do around collecting telemetry, monitoring, identifying when there were types of failures during the training. All of those things are now available to you out of the box through the SageMaker HyperPod. So this is turnkey training infrastructure, tools and libraries that do all of the checkpointing. They heal from those hard failures, also help you maximize utilization without any sort of manual intervention. So all of the work that was done to just tune the infrastructure is something that's virtually turnkey and out of the box for you today. Of course, today, NVIDIA's latest and greatest hardware that's out there right now is the H100 GPU. So you have a dramatic increase actually in the effective teraflops of throughput that each GPU can provide. Of course, Blackwell and other interesting innovations are on the horizon as well. And then one of the features we were very excited about and very vocal about when we were going through the process with AWS is making sure that FSDP support was available in SMP, the next generation of the SMP libraries from AWS. So like I mentioned before, our data science platform, which is an MLOps platform we run in-house for smaller model training and fine-tuning, we want to make sure that we can actually use code targeted for that platform in any environment that we're running in. If you want to learn more about the Bloomberg Data Science Platform and the infrastructure we've built to support this, built on top of CNCF open source projects like Kubernetes, Kubeflow, Kserve, definitely check out our team's talks at KubeCon America from a couple weeks ago. However, this innovation of making sure that we can use both on-prem code or code both on-prem as well as when we burst into AWS is extremely important for us. It makes our life a lot easier. So another important thing, and Andy said this morning, so I thought I was being clever, but it turns out this was like the obvious joke. One model does not rule them all. And you actually need to be able to select the right model for your application at a point in time, but also based on what your application requires, the strengths and weaknesses of the model specific to your use case. Some of this is really obvious stuff. How good is that model at a downstream task? You also need to consider the latency of the model and the throughput of the model. And this is actually important from a user experience perspective. If you can do the calculation up front, which is what happens with our transcript summarization product, users are not waiting on the model to execute and provide insights. However, if a user's left waiting and waiting for a result because they're asking a question dynamically, that could create a poor user experience. But also you have to ask yourself, sometimes a large language model might not be the right answer for that as well. And then, of course, a lot of folks are looking at agents and like tools to actually augment the human in the loop case as being an example of where people want to apply LLMs. But of course, the models that are suitable for that versus transcript summarization versus generating code automatically are not this one and the same. You also have to consider the approach you're taking to actually add knowledge to the model. So if you're doing RAG or fine tuning, you need to consider that model specialized essentially for that application, or you likely are going to want to make sure that that model is only used for its target application. And then, of course, you need to be continually looking at whether or not a model is actually continuing to generate good results, or if there's an opportunity to improve by iterating on fine-tuning or choosing a different model altogether. So getting into that, I want to hand this back to Vadim because we need to demand more capabilities from our AI platforms beyond just model deployment. So we're going to talk about some important infrastructure elements to deal with the shifting requirements of LLM workloads.
Thanks, Phil. So Bloomberg is an open source first company. That means we're not only using open source internally extensively, but we also contribute back to the open source, specifically in the areas like Kubernetes and ML domains. And in fact, some of the libraries, like Kserve, was born at Bloomberg. So as we started our journey to operationalize the large language model workloads, we realized that some of the existing open source solution to provide the gateway capabilities for to access your LLMs do not have the required enterprise features, such as the robust tenancy isolation, quota management and cost attribution, and some advanced routing capabilities between different inference providers. To address these gaps, Bloomberg partnered with the Envoy community to build the Envoy AI Gateway. So this solution will serve multiple enterprise use cases where the teams are looking to integrate multiple LLMs in their stack when using a single endpoint API. So the Envoy AI Gateway project is currently in active development by Bloomberg team and the teams at Tetrate, and we focused on 3 key feature set. The first one is the centralized API management. As I mentioned, multiple teams are using multiple LLMs, and these LLMs are hosted on different inference providers. In our case, it can be the internal data science platform. It can be also AWS Bedrock models. All these models, they have slightly different APIs. So the AI Gateway will address this and provide a consistent API across all the models, and that will ensure interoperability and ease the integration with the LLMs for the product teams. Another area relates to segregating and enforcing access policies across hundreds of tenants and provide robust access and compliance management capabilities. Cost and capacity management are another key aspects. The Envoy AI Gateway will provide centralized cost metering and cost attribution capabilities, as well as the quota management, where you distributed the available capacity between your tenants. It will also implement the intelligent routing solutions based on the latency we see with your LLM models, as well as your overall fleet capacity. As more and more enterprises are using multiple LLMs, solutions like Envoy AI Gateway will simplify how you integrate multiple models into your AI stack.
Thank you, Vadim. And of course, this is one of the talks we did at KubeCon, and of course, we have many more talks coming up on this topic. We're very excited about this open source capability. So I wanted to end this today, before we get into some questions, with a question. So do you actually need a custom foundation model? Do you need to train your own model? We learned this process is complex, and answering that question is not something we can give you a cookie cutter process to answer it. The good news is that if you do need to do this, and if you do want to experiment with training your own models or even train your own production models, AWS has made this even more turnkey today than it was 2 years ago. We wish that SageMaker Hyperpod was a thing when we were actually doing this, because that would have made our lives a lot easier. But think hard about whether or not you can achieve amazing results for your applications by either fine-tuning an existing open source, open weights model with your own data sets, and this is actually one of the ways that we actually unlock the power of generative AI for Bloomberg's products. By leveraging an existing large language model, one that we didn't train from scratch, and then fine-tuning that model, or using RAG to provide additional context was key. So while BloombergGPT was never meant to see the light of day for client applications, the impact of what we learned about whether or not this was the right way to solve problems for our business, as well as what we learned building and training the model, really has helped us shape our broader generative AI strategy in too many ways to count. But those 3 principles are what's driving all of our product innovation in this space today. So thank you, and I wanted to hand this off to Vasu. He's going to moderate some questions.